Imagine a light so powerful it can outshine an entire galaxy. Not a star, not a supernova, but a single point in the distant universe, brighter than hundreds of billions of suns combined. For decades, astronomers saw these strange objects flickering across the sky. They appeared impossibly bright, incredibly distant, and strangely unpredictable. Sometimes they would suddenly flare with enormous energy, then fade again into the darkness of space. No one understood what they were, until scientists realized something extraordinary. At the heart of these objects lies a supermassive black hole, millions or even billions of times heavier than our Sun. As matter spirals into this cosmic abyss, enormous jets of energy are launched outward at nearly the speed of light. And when one of those jets happens to be pointed almost directly toward Earth, we see one of the most extreme objects in the entire universe, a blazar. These cosmic engines can release more energy than entire galaxies, sending powerful beams of radiation across billions of light-years of space. Tonight, we're going to explore how blazars form, why their jets are so powerful, and what makes them some of the most violent objects ever discovered. And if you enjoy exploring the deepest mysteries of the cosmos, make sure to subscribe to Stellar Depth for more journeys into the hidden extremes of our universe. Far out in the vastness of the universe, scattered across billions of galaxies, there exist some of the most powerful engines ever discovered. These engines are not stars, planets, or even supernova explosions. Instead, they are powered by the most extreme objects known to science, supermassive black holes. At the center of almost every large galaxy lies one of these enormous black holes. Some contain millions of times the mass of our Sun. Others are far larger, reaching billions of solar masses. Most of the time, these black holes are relatively quiet. They sit at the center of their galaxies, slowly influencing the motion of nearby stars and gas through their immense gravity. But sometimes, the situation becomes dramatically different. When large amounts of gas, dust, and cosmic debris begin falling toward the black hole, an extraordinary transformation occurs. Instead of disappearing instantly into darkness, the incoming material forms a rapidly spinning structure around the black hole known as an accretion disk. This disk becomes one of the most energetic places in the entire universe. As matter spirals inward toward the black hole, it begins to move faster and faster. Friction between particles heats the material to incredible temperatures, sometimes reaching millions of degrees. At these temperatures, the gas turns into an extremely hot plasma that glows intensely across many wavelengths of light. This glowing disk becomes visible across enormous distances in space. The radiation produced in these regions is so powerful that it can outshine all the stars in the galaxy combined. Astronomers call galaxies with such energetic centers active galactic nuclei, or AGN. These active galaxies come in several different forms depending on how we observe them. Some show bright radiation from the disk surrounding the black hole. Others display enormous jets of particles shooting outward into space. But among all these active galaxies, there's one type that stands out as particularly dramatic. These are the blazars. To understand why blazars appear so powerful, we must first understand the remarkable process that occurs near a feeding supermassive black hole. Inside the accretion disk, magnetic fields become twisted and tangled, by the intense motion of the plasma. These magnetic fields act like enormous cosmic coils, storing vast amounts of energy. Under the right conditions, these fields channel some of the material away from the disk and accelerate it outward along the rotational axis of the black hole. This process creates two narrow beams of particles and radiation, known as relativistic jets. These jets are among the most extraordinary structures ever observed in the universe. Particles within these jets move at speeds extremely close to the speed of light. Because of this, they carry enormous amounts of energy as they travel outward from the black hole. The jets can extend astonishing distances into space. In some cases, they stretch for hundreds of thousands of light years, far beyond the boundaries of the host galaxy itself. Within these jets, charged particles spiral along magnetic field lines while emitting radiation across a wide range of frequencies. This radiation includes radio waves, visible light, X-rays, and even extremely energetic gamma rays. But the true reason blazars appear so powerful has to do with the direction of these jets. In most active galaxies, the jets point in random directions relative to Earth. We may observe them from the side, which allows astronomers to see the long structures extending outward from the galaxy. However, in a blazar, one of the jets is pointed almost directly toward us. This alignment produces a remarkable effect known as relativistic beaming. Because the particles in the jet are moving at nearly the speed of light, the radiation they emit becomes concentrated in the direction of motion. As a result, the light that reaches Earth is dramatically amplified. The jet essentially acts like a cosmic spotlight aimed straight at our planet. This amplification makes blazars appear incredibly bright. Even though the source may lie billions of light years away, it can still be detected by telescopes on Earth. In some cases, blazars can outshine their entire host galaxies by enormous factors. Astronomers first began identifying blazars during the early days of radio astronomy. In the mid-20th century, scientists started detecting powerful radio signals coming from distant regions of space. At first, it was unclear what objects could be producing such intense emissions. As telescopes improved, astronomers began to identify the galaxies responsible for these signals. Many of these galaxies contained extremely bright cores, suggesting that powerful activity was occurring near their centers. Further observations revealed that some of these objects also emitted strong X-ray and gamma-ray radiation. These discoveries indicated that enormous energies were involved. By the late 20th century, astronomers realized that many of these sources were actually the same type of object: active galaxies with jets pointed toward Earth. These became known as blazars. Today, blazars are recognized as some of the most extreme objects in the universe. Their jets can accelerate particles to energies far greater than anything produced in human-made particle accelerators. These particles can travel across intergalactic space, sometimes interacting with cosmic radiation fields along the way. The jets also vary in brightness over time. Unlike most galaxies, which change slowly over millions or billions of years, blazars can change dramatically within hours or even minutes. This rapid variability reveals important clues about the size of the regions producing the radiation. If a blazar brightens within a short period of time, it means the source of the emission must be relatively small. Otherwise, the light could not change so quickly. Observations show that much of the radiation likely originates from regions only a few light hours across. Considering that these regions lie near black holes containing billions of solar masses, this scale is remarkably compact. The intense radiation produced by blazars also allows scientists to study the structure of the universe itself. As light from a distant blazar travels through space, it passes through clouds of gas, dust, and other cosmic structures. These materials leave subtle signatures in the light, allowing astronomers to study the composition and distribution of matter across the universe. In this way, blazars act as powerful beacons illuminating the cosmos. By studying them, astronomers can learn not only about the extreme physics near supermassive black holes, but also about the vast cosmic structures that fill the universe. Blazars therefore represent far more than just violent cosmic objects. They are windows into some of the most energetic processes in existence. From the twisting magnetic fields near black holes to the enormous jets that stretch across galaxies, blazars reveal the incredible power hidden within the darkest regions of space. And as scientists continue to observe these extraordinary objects with ever more advanced telescopes, they are beginning to uncover the deeper secrets of how the universe produces such astonishing energy. Because when a supermassive black hole begins to feed, and its jet happens to point directly at Earth, the result is one of the most dramatic spectacles the cosmos has to offer. To understand why blazars are so powerful, we must look deeper into the environment surrounding the supermassive black hole that powers them. These black holes are not simply empty voids in space that swallow everything nearby. Instead, they are surrounded by one of the most energetic regions in the entire universe. When gas and dust fall toward a supermassive black hole, the material does not immediately disappear into the event horizon, because this matter usually possesses some angular momentum. It begins to orbit the black hole rather than falling straight inward. As more and more material accumulates, it forms a rotating disk around the black hole. This structure is known as an accretion disk. Inside the accretion disk, matter moves at incredible speeds. The inner regions of the disk can orbit the black hole at a significant fraction of the speed of light. As particles move through the disk, they collide with each other and generate intense friction. This friction heats the material to extreme temperatures. The result is a disk of superheated plasma that glows brilliantly across the electromagnetic spectrum. Some parts of the disk shine brightly in visible light, while other regions emit powerful X-rays and ultraviolet radiation. In fact, the radiation produced by the accretion disk can be so intense that the core of the galaxy becomes far brighter than all the stars surrounding it. This phenomenon is what defines an active galactic nucleus, or AGN. But the accretion disk alone does not explain the most dramatic features of blazars. To understand those features, we must examine the role of magnetic fields. The plasma inside the accretion disk contains charged particles. Whenever charged particles move, they generate magnetic fields. As the disk rotates, these magnetic fields become twisted and stretched into complex shapes. Over time, the magnetic field lines can become tightly wound around the black hole. This twisting of magnetic fields stores enormous amounts of energy. Under certain conditions, the magnetic fields can channel some of the material away from the disk and accelerated outward along the rotational axis of the black hole. This process forms the enormous jets that define blazars. These jets emerge from regions very close to the black hole, where gravity and magnetic forces interact in extremely complex ways. The exact mechanism responsible for launching these jets is still being studied by scientists, but several leading theories have been proposed. One widely accepted model is known as the Blandford-Znajek mechanism. According to this theory, the rotation of the black hole itself plays a crucial role in powering the jet. If the black hole is spinning rapidly, it can transfer some of its rotational energy to the surrounding magnetic fields. These magnetic fields then accelerate particles outward along the black hole's poles, producing powerful jets. Another possible process involves the accretion disk itself. In this scenario, magnetic fields anchored in the disk can fling particles outward through a process similar to a cosmic slingshot. As the disk rotates, the magnetic field lines act like tensioned wires, launching particles away from the disk at incredible speeds. Regardless of the exact mechanism, the result is the same. Narrow beams of energetic particles are expelled from the black hole's surroundings at speeds approaching the speed of light. These relativistic jets are among the most extraordinary structures in the universe. They can travel vast distances through intergalactic space. In some galaxies, jets have been observed extending for hundreds of thousands of light years. As these jets travel through space, they interact with the surrounding gas and dust. The high-speed particles within the jets collide with magnetic fields and emit radiation through a process known as synchrotron radiation. This radiation produces the bright glow that astronomers detect with telescopes. Synchrotron radiation occurs when charged particles spiral around magnetic field lines at extremely high speeds. The faster the particles move, and the stronger the magnetic field, the more energetic the radiation becomes. Because of this process, jets can emit radiation across an enormous range of wavelengths. Radio telescopes detect the long wavelength radio emissions produced by the jets. Optical telescopes capture visible light emitted by energetic particles. Meanwhile, X-ray and gamma-ray observatories detect the highest energy radiation produced by the most extreme particle collisions. In blazars, the radiation from these jets appears especially intense. This is because one of the jets is directed almost exactly toward Earth. When particles move at speeds close to the speed of light, strange relativistic effects occur. One of these effects is known as relativistic beaming. Relativistic beaming causes the radiation emitted by fast-moving particles to become concentrated in the direction of their motion. Imagine a flashlight attached to a rapidly moving spacecraft. As the spacecraft moves forward, the beam of light becomes compressed and focused in the direction of travel. A similar effect occurs in blazar jets. Because the particles are traveling so quickly, the radiation they emit becomes highly concentrated along the direction of the jet. If that jet happens to be pointed toward Earth, the radiation we observe becomes dramatically amplified. This amplification makes blazars appear extraordinarily bright. Even though the galaxy containing the blazar may lie billions of light years away, the radiation from the jet can still reach Earth with remarkable intensity. Another consequence of relativistic beaming is the appearance of rapid variability. Blazars often fluctuate in brightness over extremely short periods of time. Astronomers have observed blazars that change their brightness dramatically within hours or even minutes. These rapid changes suggest that the region producing the radiation must be relatively small. If the emitting region were very large, it would take much longer for the brightness to change across the entire area. The rapid variability observed in blazars therefore indicates that much of the radiation originates from regions very close to the central black hole. In addition to synchrotron radiation, blazars also produce extremely high-energy gamma rays through other physical processes. One of these processes is known as inverse Compton scattering. In this process, high-energy electrons collide with lower-energy photons. When the electrons transfer energy to the photons become dramatically more energetic. This interaction can transform relatively low-energy light into powerful gamma rays. Because of these processes, blazars are among the most powerful gamma-ray sources in the universe. Space telescopes designed to detect gamma rays have observed blazars emitting photons with energies far beyond anything produced in ordinary stars. Some of these photons carry energies millions or even billions of times greater than visible light. These observations provide valuable information about the extreme environments near supermassive black holes. By studying the radiation emitted by blazars, scientists can learn about the behavior of matter and energy under conditions that cannot be recreated in laboratories on Earth. Blazars therefore serve as cosmic laboratories, where the laws of physics are tested at their limits. They reveal how magnetic fields interact with gravity, how particles are accelerated to extreme energies, and how black holes influence the galaxies that surround them. In the next part of this documentary, we will explore how astronomers discovered blazars and how modern telescopes are helping scientists uncover the secrets of these incredible cosmic powerhouses. The story of how blazars were discovered is closely tied to the development of modern astronomy and the rise of radio telescopes in the 20th century. Before that time, astronomers studied the universe almost entirely through visible light. Telescopes revealed stars, galaxies, nebulae, and planets, but much of the universe remained hidden, simply because many cosmic objects emit energy in wavelengths invisible to the human eye. Everything began to change when scientists started exploring the sky using radio waves. Radio astronomy emerged during the 1930s and 1940s, when researchers realized that certain cosmic objects produced strong radio signals. Early radio telescopes detected powerful sources of radiation coming from distant regions of space. At first, these mysterious signals were difficult to identify because radio telescopes lacked the resolution needed to pinpoint their exact locations. However, as technology improved, astronomers began to map the radio sky with greater accuracy. They soon discovered that some of the strongest radio sources were associated with distant galaxies. These galaxies did not appear particularly unusual in visible light, yet their centers emitted enormous amounts of radio energy. One of the most famous early discoveries occurred in the 1960s, when astronomers identified a strange class of objects known as quasars, short for quasi-stellar radio sources. At first, quasars looked like ordinary stars in telescope images. They appeared as small points of light, rather than extended galaxies. But when astronomers studied their spectra, the distribution of light across different wavelengths, they noticed something remarkable. The spectral lines from these objects were shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs when objects move away from us as the universe expands. The greater the redshift, the farther away the object must be. To the astonishment of astronomers, the redshift measurements revealed that quasars were located billions of light-years away. Despite these enormous distances, they appeared extremely bright. In fact, some quasars were brighter than entire galaxies. This meant they were releasing staggering amounts of energy. As scientists studied these objects further, they realized that quasars were powered by supermassive black holes surrounded by luminous accretion disks. The immense energy released by matter falling into the black hole explained their extraordinary brightness. But another puzzle soon emerged. Some of these active galaxies produced enormous jets of particles that extended far beyond the galaxy itself. These jets emitted strong radio signals and could stretch for hundreds of thousands of light-years into intergalactic space. Astronomers began to notice that some of these objects displayed unusual variability. Unlike normal galaxies, whose brightness changes very slowly over millions of years, certain active galaxies fluctuated rapidly. Their brightness could rise or fall dramatically within days, hours, or even minutes. These rapid changes suggested that the source of the radiation must be extremely compact. If the emitting region were very large, it would take much longer for the brightness to change across the entire structure. This led astronomers to suspect that the radiation was coming from a very small region near the central black hole. In the late 20th century, scientists began to recognize that many of these highly variable objects belong to a special category of active galaxies. These were eventually named Blazars. Blazars are essentially active galaxies whose relativistic jets are pointed almost directly toward Earth. Because the jet is aimed at us, the radiation becomes amplified by relativistic effects. This amplification explains why blazars appear so extraordinarily bright. It also explains why they exhibit such dramatic variability. Even small changes within the jet can produce noticeable changes in brightness when the radiation is directed straight toward us. Astronomers classify blazars into two main categories. The first group is known as BL Lacertae objects, named after a particular object discovered in the constellation Lacerta. BL Lac objects display very weak or almost non-existent emission lines in their spectra, making them difficult to study using traditional spectroscopic techniques. The second group is known as flat spectrum radio quasars, or FSRQs. These objects resemble quasars in many ways but display strong radio emission and powerful relativistic jets. Although BL Lac objects and flat-spectrum radio quasars have different observational characteristics, scientists believe they are powered by the same fundamental mechanism: a supermassive black hole with a jet pointing toward Earth. Modern telescopes have allowed astronomers to observe blazars across the entire electromagnetic spectrum. Radio telescopes reveal the long structures of the jets. Optical telescopes capture visible light emitted by energetic particles. X-ray telescopes detect high-energy radiation produced near the base of the jet. Gamma-ray observatories observe the most energetic photons produced in the extreme environment near the black hole. One of the most important instruments for studying blazars is NASA's Fermi Gamma Ray Space Telescope. Launched in 2008, the Fermi telescope has detected hundreds of blazars emitting powerful gamma rays. These observations have revealed that blazars are among the most dominant sources of gamma radiation in the sky. Gamma rays represent the highest energy form of light, far more energetic than visible light or X-rays. The fact that blazars produce such intense gamma-ray emission indicates that particles within their jets are being accelerated to incredible energies. Some of these particles may carry energies millions of times greater than those produced by the most powerful particle accelerators on Earth. Understanding how these particles achieve such enormous energies remains one of the major challenges in modern astrophysics. Another remarkable feature of blazars is their polarization. Light waves can vibrate in different directions, and when these vibrations become aligned, the light is said to be polarized. Observations show that the radiation from blazars is often strongly polarized. This polarization provides important clues about the structure of the magnetic fields within the jet. Because synchrotron radiation is produced by particles spiraling along magnetic field lines, the direction of polarization reveals how those magnetic fields are arranged. By measuring polarization, astronomers can map the magnetic structure of the jet and study how it evolves over time. This information helps scientists understand how jets remain stable over enormous distances. Blazars also provide important clues about the large-scale structure of the universe. Because they are so bright, they can be observed across extremely large cosmic distances. Some known blazars lie billions of light-years away, meaning the light we see today left those objects when the universe was much younger. By studying the light from these distant blazars, astronomers can learn about the conditions that existed in the early universe. For example, as the light travels toward Earth, it passes through clouds of gas between galaxies. These clouds absorb certain wavelengths of light, leaving distinctive signatures in the blazar's spectrum. By analyzing these absorption features, scientists can map the distribution of matter across the universe. Blazars therefore act like cosmic flashlights shining through intergalactic space. Their powerful beams illuminated the invisible structures that fill the universe. This makes them valuable tools not only for studying black holes and jets, but also for exploring the large-scale architecture of the cosmos. Over the past few decades, the study of blazars has transformed our understanding of how supermassive black holes interact with their host galaxies. Rather than being passive objects, these black holes can influence their surroundings through powerful jets and radiation. These jets can heat gas within the galaxy, regulate star formation, and even affect the growth of the galaxy itself. In this way, blazars demonstrate that supermassive black holes play a central role in shaping the evolution of galaxies. And as new telescopes continue to observe these extraordinary objects with increasing precision, scientists are uncovering more and more details about the violent processes occurring near the most powerful engines in the universe. At the heart of every blazar lies a phenomenon that challenges our understanding of gravity, energy, and motion: the presence of a supermassive black hole actively consuming matter. While black holes themselves cannot be seen directly, Their influence on surrounding material creates some of the most energetic environments in the universe. The central black holes that power blazars are enormous. Most contain millions to billions of times the mass of the Sun. Despite this tremendous mass, the black hole itself occupies a surprisingly small region of space. The boundary beyond which nothing can escape its gravity is called the event horizon, and for even the largest supermassive black holes, this region may be only a few times larger than the orbit of Mercury around the Sun. Yet the true power of a blazar comes not from the black hole alone, but from the chaotic environment surrounding it. As gas, dust, and stray stars drift toward the center of a galaxy, the immense gravity of the black hole pulls this material inward. However, because the material usually possesses angular momentum, it does not fall directly into the black hole. Instead, it begins to orbit the black hole at extremely high speeds. This orbiting matter forms the accretion disk. The accretion disk is one of the brightest and most energetic structures in the universe. Within this disk, particles move so quickly that collisions between them generate enormous amounts of heat. Temperatures in the inner regions can reach tens of millions of degrees. At these temperatures, atoms are stripped of their electrons, and the gas becomes a glowing plasma. The plasma emits intense radiation across many wavelengths of light, from visible light to ultraviolet and X-rays. In powerful active galaxies, the radiation from the accretion disk alone can outshine all the stars in the host galaxy combined. But the accretion disk is only part of the story. Surrounding this disk are extremely strong magnetic fields. These magnetic fields are created by the motion of charged particles within the plasma. As the disk rotates around the black hole, the magnetic field lines become twisted and stretched. Over time, the fields become increasingly tangled and powerful. These magnetic fields play a critical role in the formation of the enormous jets that define blazars. Under certain conditions, the magnetic field lines become so tightly wound that they act like enormous cosmic springs. The stored magnetic energy can then accelerate particles away from the disk and launch them outward along the poles of the black hole. This produces two narrow beams of energetic particles traveling in opposite directions. These beams are known as relativistic jets. The particles inside these jets travel at speeds extremely close to the speed of light. Because of these incredible speeds, the jets carry enormous amounts of energy as they shoot out into intergalactic space. The exact process responsible for launching these jets is still one of the most active areas of research in astrophysics. One important theory involves the rotation of the black hole itself. Many supermassive black holes spin rapidly due to the accumulation of matter over billions of years. If a black hole is spinning, it can drag the surrounding space around with it, a phenomenon predicted by Einstein's theory of general relativity, known as frame dragging. In this scenario, magnetic fields anchored in the surrounding accretion disk interact with the spinning black hole. The rotation of the black hole twists the magnetic fields even further, transferring some of the black hole's rotational energy into the jet. This process can accelerate particles to extraordinary energies. Another possible mechanism involves magnetic forces within the accretion disk itself. In this model, the rotating disk acts like a giant electromagnetic generator. the magnetic field lines anchored in the disk fling particles outward, similar to how a rotating sprinkler sprays water outward. Regardless of the precise mechanism, the result is the same. Enormous jets of plasma are launched from the vicinity of the black hole, traveling vast distances through space. These jets can extend far beyond the galaxy that contains them. In some cases, astronomers have observed jets stretching hundreds of thousands of light years into intergalactic space. These structures are among the largest coherent structures known in the universe. Within the jets, charged particles spiral along magnetic field lines while emitting radiation through a process known as synchrotron radiation. Synchrotron radiation occurs when high-speed charged particles move through magnetic fields. As they spiral around the field lines, they release energy in the form of electromagnetic radiation. This radiation is responsible for much of the visible glow observed in relativistic jets. The radiation produced by synchrotron processes spans a wide range of wavelengths. Radio telescopes detect the lower energy emissions, while optical and X-ray telescopes capture higher energy radiation from more energetic particles. In the case of blazars, the radiation becomes especially intense because the jet is aimed almost directly toward Earth. This alignment produces the effect known as relativistic beaming. When particles move at speeds close to the speed of light, the radiation they emit becomes concentrated in the direction of their motion. As a result, the light emitted by the jet becomes strongly amplified along its path. If the jet is pointed toward Earth, the radiation appears dramatically brighter than it would otherwise. This effect can make a distant blazar appear brighter than an entire galaxy filled with billions of stars. The brightness of blazars is not constant. In fact, one of the most remarkable features of these objects is their rapid variability. Astronomers have observed blazars that suddenly brighten or fade within very short periods of time. Some fluctuations occur over days or hours, while others can happen within minutes. These rapid changes provide important clues about the size of the regions producing the radiation. Because light cannot travel instantaneously across large distances, any rapid change in brightness must originate from a relatively small region. This suggests that much of the radiation we observe from blazars comes from areas very close to the central black hole. These regions may be only a few light hours across, incredibly small compared with the vast size of the galaxy itself. Another important aspect of blazar jets is the way they accelerate particles to extreme energies. Within the jet, shock waves can form when faster-moving material collides with slower-moving plasma. These shock waves can accelerate particles through a process known as Fermi acceleration. During this process, particles bounce back and forth across the shock front, gaining energy with each pass. Eventually, some particles reach energies far greater than those produced in any human-made particle accelerator. These extremely energetic particles can then interact with surrounding radiation fields, producing high-energy gamma rays. Gamma rays represent the most energetic form of electromagnetic radiation. They carry enormous amounts of energy and are capable of traveling across vast distances through space. Many blazars are powerful sources of gamma rays, making them important targets for space telescopes designed to detect high-energy radiation. The detection of gamma rays from blazars provides valuable insights into the processes occurring within the jet. By studying these emissions, astronomers can learn how particles are accelerated, how magnetic fields shape the jet, and how energy is transported away from the black hole. Blazars therefore serve as natural laboratories for studying physics under extreme conditions. They allow scientists to investigate the behavior of matter moving at relativistic speeds, the interaction between magnetic fields and plasma, and the powerful effects of gravity near supermassive black holes. In the next part of this documentary, we will explore how blazars influence their surrounding galaxies and how these powerful jets can shape the evolution of entire cosmic structures. The immense power of blazars does not remain confined to the region surrounding the black hole. The jets they produce can travel enormous distances, interacting with the surrounding galaxy and even the intergalactic space beyond it. Because of this, blazars are not only fascinating objects on their own, they also play an important role in shaping the evolution of galaxies and the environments around them. To understand this influence, we must first consider the scale of the jets produced by these active galaxies. Although the region where the jet originates is extremely small compared to the size of a galaxy, the jet itself can extend across distances that are truly staggering. In some cases, astronomers have observed relativistic jets stretching hundreds of thousands of light years from the center of their host galaxy. For comparison, the diameter of the Milky Way galaxy is about 100,000 light years. This means that some jets are long enough to travel completely beyond the boundaries of the galaxy that created them. As the jet moves outward through space, it does not travel through empty vacuum. Instead, it encounters clouds of gas, dust, and diffuse plasma that exist throughout the galaxy and the surrounding intergalactic medium. The high-energy particles within the jet collide with this material, producing shock waves and heating the surrounding gas. These interactions can create enormous structures known as radiolobes. Radiolobes are giant clouds of energized particles located at the ends of the jets. When the jet collides with the surrounding medium, the particles slow down and spread outward, inflating large, bubble-like regions of plasma. These lobes emit strong radio waves through synchrotron radiation, allowing astronomers to observe them with radio telescopes. Some radiolobes are among the largest known structures associated with galaxies. In certain cases, the lobes can span distances greater than 1,000,000 light years from one end to the other. These enormous structures reveal just how much energy is being pumped into the surrounding environment by the central black hole. The influence of these jets extends far beyond simply creating glowing radio structures. They can also affect the gas within the host galaxy itself. Galaxies contain vast reservoirs of gas that serve as the raw material for forming new stars. When gas clouds collapse under gravity, they can produce clusters of young stars that illuminate the galaxy. However, the powerful jets from an active galactic nucleus can disrupt this process. As the jets travel through the galaxy, they can heat the surrounding gas to extremely high temperatures. When gas becomes too hot, it becomes more difficult for gravity to pull it together into dense clouds capable of forming stars. In this way, the jets may suppress star formation within the galaxy. Astronomers refer to this process as AGN feedback. AGN feedback plays an important role in modern theories of galaxy evolution. It helps explain why some massive galaxies appear to contain very little ongoing star formation. The central black hole may effectively regulate the growth of the galaxy by heating and dispersing the gas that would otherwise form new stars. However, the effects of jets are not always destructive. In some situations, the shock waves produced by the jet can actually compress gas clouds rather than disperse them. This compression may trigger bursts of star formation in certain regions of the galaxy. Thus, the influence of a Blazar's jet can be complex, sometimes suppressing star formation and sometimes stimulating it. The interaction between jets and their environments is therefore an important topic of study in astrophysics. Another remarkable aspect of Blazar jets is their ability to transport energy across enormous distances. The particles within the jet carry vast amounts of kinetic energy as they move outward from the black hole. When these particles collide with surrounding material, they transfer some of this energy into the surrounding gas. Over time, this energy can reshape the structure of the galaxy's surrounding environment. For example, the hot gas found in clusters of galaxies may be heated by jets from active galactic nuclei. Galaxy clusters are enormous structures containing hundreds or even thousands of galaxies bound together by gravity. Between these galaxies lies a vast reservoir of extremely hot gas known as the intra-cluster medium. Observations show that this gas remains hot for extremely long periods of time. Without an ongoing source of energy, the gas would gradually cool and collapse toward the center of the cluster. However, jets from active galaxies appear to inject enough energy into the gas to prevent this collapse. In this way, the activity of supermassive black holes can influence not only individual galaxies, but entire clusters of galaxies. Blazars therefore represent one of the most powerful examples of how black holes shape the large-scale structure of the universe. Another intriguing consequence of Blazar activity involves the production of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. Many cosmic rays originate from supernova explosions within our galaxy, but some of the most energetic cosmic rays may come from extragalactic sources. Blazars are strong candidates for producing these extremely high-energy particles. Within the jet, particles are accelerated by magnetic fields and shock waves to extraordinary energies. Some of these particles escape the jet and travel across intergalactic space. Eventually, a small fraction of these particles may reach Earth. Although the journey across billions of light years is extremely difficult for these particles, the detection of ultra-high-energy cosmic rays suggests that powerful sources such as blazars may be responsible for their origin. Studying cosmic rays from blazars provides valuable information about the extreme conditions within the jets. It also helps scientists understand how energy moves across the universe on the largest scales. Blazars are also important for studying the distribution of matter across the universe. Because they are so bright, blazars can be observed at enormous distances. Light from distant blazars must travel through vast regions of intergalactic space before reaching Earth. Along the way, this light interacts with clouds of gas and dust between galaxies. These interactions leave subtle absorption features in the blazar's spectrum. By studying these features, astronomers can identify the presence of otherwise invisible gas clouds. This allows scientists to map the distribution of matter between galaxies and study how the universe is structured on large scales. Blazars therefore act as powerful cosmic beacons. Their bright jets illuminate the space between galaxies, allowing astronomers to study regions that would otherwise remain hidden. Another important discovery involving blazars is their connection to high-energy neutrinos. Neutrinos are extremely tiny particles that interact very weakly with matter. Because of this, they can travel enormous distances through the universe without being absorbed. Detecting neutrinos from distant sources is extremely difficult, but specialized detectors have begun to observe them. In recent years, scientists detected high-energy neutrinos that appear to have originated from a distant blazar. This discovery provided evidence that the jets of blazars may accelerate not only electrons, but also protons and other heavy particles. When these particles collide with radiation or other particles within the jet, they can produce neutrinos. The detection of neutrinos from blazars opens an entirely new way of studying these objects. Unlike photons, neutrinos travel through space almost completely unaffected by intervening matter or magnetic fields. This means they carry direct information about the processes occurring inside the jet. By combining observations of neutrinos, gamma rays, and other forms of radiation, scientists can build a more complete picture of how blazars operate. In this way, blazars are not only fascinating cosmic phenomena, but also powerful tools for exploring the universe. They reveal how supermassive black holes interact with their galaxies, how energy is transported across cosmic distances, and how extreme physical processes shape the evolution of the cosmos. In the next part of this documentary, we will explore some of the most famous blazars ever discovered and examine how astronomers observe these extraordinary objects using modern telescopes across the electromagnetic spectrum. Throughout the history of modern astronomy, several blazars have become especially important to scientists because they provide clear examples of how these extraordinary objects behave. By studying these specific sources in detail, astronomers have been able to uncover many of the physical processes that occur near supermassive black holes and inside relativistic jets. One of the most famous blazars ever discovered is B.L. Lacertae, located in the constellation Lacerta. This object was first identified in the early 20th century and initially confused astronomers because it appeared similar to an ordinary star when observed with optical telescopes. Unlike galaxies, which typically appear as extended fuzzy structures in the sky, B.L. Lacertae looked like a single point of light. For many years, scientists believed it might simply be a variable star within our own galaxy. However, as more detailed observations were made, astronomers realized something very unusual about its light. Most astronomical objects produce characteristic spectral lines that reveal the presence of specific elements such as hydrogen, helium, or oxygen. These lines allow scientists to determine the composition and motion of distant objects. B.L. Lacertae, however, showed almost no spectral lines at all. Its spectrum appeared nearly featureless, which made it extremely difficult to determine its distance or physical properties. This strange behavior puzzled astronomers for decades. Eventually, improved observations revealed that B.L. Lacertae was not a nearby star but a distant galaxy, whose central region was dominated by powerful radiation from a relativistic jet pointed almost directly toward Earth. Because the jet was aimed at us, the intense radiation overwhelmed the light from the rest of the galaxy, making it appear star-like in early observations. Objects with similar characteristics were eventually grouped into a category known as BL-LAC objects, named after this original example. BL-LAC objects are now recognized as one of the two main types of blazars. They are characterized by strong variability, high polarization of their light, and weak or absent spectral lines. Another famous blazar is 3C273, one of the first quasars ever identified. Located in the constellation Virgo, 3C273 lies about 2.4 billion light-years away from Earth. Despite this enormous distance, it is bright enough to be observed with relatively small telescopes. 3C273 produces enormous jets of particles that extend far beyond its host galaxy. High-resolution images from radio telescopes reveal long streams of glowing plasma stretching across tens of thousands of light-years. These jets emit radiation across a wide range of wavelengths, allowing astronomers to study them using radio, optical, X-ray, and gamma-ray telescopes. Another remarkable blazar is TXS 0506 plus 056, which became famous in 2018 when scientists detected a high-energy neutrino originating from its direction. This discovery marked a major milestone in astrophysics. For the first time, researchers were able to link a high-energy neutrino directly to a specific cosmic source. The neutrino was detected by the Ice Cube Neutrino Observatory, a massive detector buried deep within the Antarctic ice. Ice Cube is designed to observe rare interactions between neutrinos and atomic nuclei. Because neutrinos interact so weakly with matter, detecting them requires enormous detectors and long observation times. When Ice Cube detected the neutrino from TXS 0506 plus 056, astronomers around the world quickly turned their telescopes toward the Blazar. Observations across multiple wavelengths revealed that the Blazar was undergoing an intense flare at the time of the neutrino detection. This strongly suggested that the same processes producing gamma rays in the jet were also generating high-energy neutrinos. The discovery provided important evidence that blazars accelerate not only electrons, but also protons and heavier particles to extremely high energies. When these high-energy particles collide with radiation or other particles within the jet, they can produce neutrinos and other secondary particles. This process links blazars to the study of cosmic rays, which are high-energy particles constantly striking Earth from space. Some of the most energetic cosmic rays ever detected may originate from powerful sources such as blazars. Observations of blazars rely on a wide range of modern telescopes and observatories. Radio telescopes are used to map the structure of the jets and radio lobes produced by the blazar. These instruments can detect the long streams of synchrotron radiation emitted by charged particles spiraling around magnetic fields. Optical telescopes observe visible light from the blazar and measure changes in brightness over time. X-ray observatories detect high-energy radiation emitted from regions near the base of the jet, where particles are being accelerated to extremely high energies. Gamma-ray telescopes, such as NASA's Fermi Gamma Ray Space Telescope, observe the most energetic photons produced by blazars. These gamma rays provide important clues about the processes occurring inside the relativistic jets. In addition to space-based observatories, ground-based instruments known as Cherenkov telescopes are used to detect very high-energy gamma rays. When gamma rays enter Earth's atmosphere, they produce cascades of secondary particles that emit faint flashes of blue light known as Cherenkov radiation. Telescopes such as HESS, MAGIC, and Veritas detect these flashes and allow scientists to study extremely energetic gamma rays from blazars. By combining observations from all these instruments, astronomers can build a detailed picture of how blazars behave across the electromagnetic spectrum. These observations have revealed that blazars often exhibit dramatic changes in brightness, known as flares. During a flare, the brightness of the blazar can increase dramatically within a short period of time. Some flares last for days or weeks, while others occur within hours. These rapid changes suggest that the region producing the radiation is extremely compact. In some cases, the variability indicates that the emission region may be only a few light hours across. Considering that this region lies near a black hole containing billions of solar masses, this is remarkably small. The study of blazar variability provides important insights into the internal structure of the jet. Changes in brightness may be caused by shock waves moving through the jet, magnetic reconnection events, or changes in the flow of plasma near the black hole. Each flare provides valuable information about the physical conditions within the jet. Another fascinating aspect of blazars is their strong polarization. Polarization occurs when the oscillations of light waves become aligned in a particular direction. Synchrotron radiation produced by particles spiraling around magnetic field lines is naturally polarized. By measuring the polarization of light from blazars, astronomers can study the structure of the magnetic fields within the jet. These measurements reveal that the magnetic fields are often highly organized, suggesting that they play a crucial role in shaping and stabilizing the jet. In some cases, the direction of polarization changes over time, indicating that the magnetic field structure is evolving. Studying these changes helps scientists understand how energy flows through the jet and how particles are accelerated to extreme energies. Blazars therefore represent some of the most dynamic and powerful objects in the universe. Their enormous jets, intense radiation, and rapid variability provide scientists with valuable clues about the behavior of matter and energy near supermassive black holes. By observing famous blazars such as B.L. Lacerte 3C273 and TXS 0506 plus 056, astronomers are gradually unraveling the mysteries of these cosmic powerhouses. And as new telescopes continue to observe the universe with increasing sensitivity, the study of blazars will undoubtedly reveal even more about the extreme processes shaping the cosmos. Blazars are not only among the most energetic objects in the universe, they are also some of the most unpredictable. Unlike most astronomical objects that change slowly over thousands or millions of years, blazars can vary dramatically in brightness over extremely short periods of time. These rapid fluctuations have fascinated astronomers for decades and provide important clues about the powerful processes occurring near supermassive black holes. One of the most striking characteristics of blazars is their extreme variability. Astronomers have observed blazars that suddenly brighten or fade within hours, days, or even minutes. These sudden changes are known as flares, and they can occur across multiple wavelengths of light, including radio waves, visible light, X-rays, and gamma rays. When a flare occurs, the brightness of the blazar can increase by several times within a very short period. After reaching its peak, the brightness may gradually decrease again as the energy released during the flare dissipates. These dramatic changes provide valuable information about the size and structure of the regions producing the radiation. Because light travels at a finite speed, a region of space cannot change brightness faster than it takes light to travel across that region. If a blazar brightens within just a few hours, it means the source of the emission must be relatively small. Otherwise, different parts of the region would brighten at different times. Using this principle, astronomers estimate that many of the flares observed in blazars originate from regions only a few light hours across. This is astonishingly small when compared to the enormous size of the galaxy containing the blazar. These compact emission regions are believed to exist near the base of the relativistic jet, close to the central supermassive black hole. Within this region, magnetic fields, high-energy particles, and intense radiation interact in extremely complex ways. Several physical processes may trigger these flares. One possibility involves shock waves traveling through the jet. Jets are not smooth streams of plasma. Instead, they often contain irregularities in density and velocity. Faster-moving material can collide with slower-moving plasma ahead of it, creating powerful shock waves. These shock waves compress and heat the plasma, accelerating particles to higher energies. As the particles gain energy, they emit more radiation, producing a bright flare. Another possible cause of flares involves magnetic reconnection. Magnetic reconnection occurs when magnetic field lines that are twisted and stretched suddenly snap and reconnect in a different configuration. This process releases large amounts of stored magnetic energy in a very short time. Magnetic reconnection events are known to occur in many astrophysical environments, including the Sun. On the Sun, magnetic reconnection is responsible for solar flares and coronal mass ejections. In blazars, similar processes may occur on a much larger scale within the relativistic jet. When magnetic reconnection occurs, enormous amounts of energy can be transferred to nearby particles, accelerating them to extremely high speeds. These energetic particles then produce intense bursts of radiation. Because the magnetic fields near the base of the jet are extremely strong and complex, reconnection events may occur frequently, leading to repeated flares. Another important factor influencing variability is the relativistic motion of the jet itself. Particles within the jet travel at speeds extremely close to the speed of light. When objects move at such speeds, unusual effects predicted by Einstein's theory of relativity begin to appear. One of these effects is time compression. Because the jet is moving toward Earth at nearly the speed of light, the radiation emitted by the jet appears compressed in time. This means that events occurring over longer periods near the source may appear to happen much faster when observed from Earth. This effect makes the variability of blazars appear even more dramatic. Another consequence of relativistic motion is relativistic boosting. radiation emitted by particles moving toward the observer becomes amplified, making the jet appear much brighter than it would otherwise. At the same time, radiation emitted in other directions becomes weaker. This is why blazars appear so extraordinarily bright compared with other active galaxies. The combination of relativistic boosting and rapid particle acceleration makes blazars some of the most luminous objects in the universe. Some blazars can produce bursts of gamma rays that briefly outshine all other sources of gamma radiation in the sky. Gamma rays represent the most energetic form of electromagnetic radiation. They are produced when extremely energetic particles interact with photons or magnetic fields. Because gamma rays carry so much energy, they provide valuable information about the most extreme processes occurring within the jet. Space telescopes, such as the Fermi Gamma Ray Space Telescope, continuously monitor the sky for gamma ray activity. These instruments have detected hundreds of blazars producing powerful gamma ray emissions. During particularly intense flares, the gamma ray brightness of a blazar can increase dramatically. These events allow astronomers to study particle acceleration and energy transfer in unprecedented detail. Another fascinating aspect of blazar variability involves the rotation of polarization. As mentioned earlier, synchrotron radiation emitted by charged particles spiraling around magnetic field lines is naturally polarized. The direction of polarization reflects the orientation of the magnetic field in the emitting region. During certain flares, astronomers observe a gradual rotation in the direction of polarization. This suggests that the magnetic field structure within the jet is changing over time. Such changes may occur when a blob of plasma moves through a twisted magnetic field, or when the geometry of the jet itself changes slightly. These observations provide valuable clues about the internal structure of the jet and the behavior of magnetic fields near the black hole. In addition to short-term flares, blazars may also exhibit long-term cycles of activity. Over periods of years or decades, the brightness of a blazar may gradually increase or decrease. These long-term changes may be related to variations in the rate at which matter falls into the black hole. If the supply of gas feeding the accretion disk increases, the disk may become brighter and inject more energy into the jet. This increased energy can produce stronger radiation and more frequent flares. Conversely, if the flow of material decreases, the jet may weaken and the blazar may become less active. Some astronomers believe that certain blazars may also contain binary supermassive black holes. In these systems, two black holes orbit each other within the same galaxy. As they interact gravitationally, they may influence the flow of gas feeding the accretion disk. This interaction could produce periodic changes in the brightness of the blazar. Although evidence for binary supermassive black holes in blazars remains limited, ongoing observations may eventually reveal such systems. The unpredictable behavior of blazars makes them both challenging and exciting objects to study. Astronomers often organize international observing campaigns to monitor blazars across multiple wavelengths simultaneously. Radio telescopes, optical observatories, X-ray satellites, and gamma-ray detectors all work together to capture different aspects of blazar activity. These coordinated observations allow scientists to track how energy moves through the jet and how different emission processes interact. by combining data from many different instruments, researchers can build detailed models of the physical processes occurring near the black hole. Through these studies, astronomers are gradually uncovering the mechanisms that drive the violent variability of blazars. Each flare, each burst of radiation, and each change in polarization provides new clues about how matter behaves under the extreme conditions near supermassive black holes. Blazars therefore represent not only some of the most powerful objects in the universe, but also some of the most dynamic. Their unpredictable flares and rapid changes reveal a constantly evolving environment where gravity, magnetism, and relativistic physics interact in spectacular ways. In the next part of this documentary, we will explore how blazars help scientists study the large-scale structure of the universe and how their powerful radiation can travel across billions of light-years to reach our telescopes. Blazars are not only fascinating because of their incredible power and violent activity, they are also extremely valuable tools for studying the universe on the largest possible scales. Because blazars are so bright, they can be observed from enormous distances across the cosmos. Some of the blazars astronomers study today are located billions of light-years away, meaning the light we observe from them began its journey when the universe was much younger. This makes blazars powerful cosmic beacons. Their bright jets shine across intergalactic space, allowing astronomers to study regions of the universe that would otherwise remain invisible. As the radiation from a distant blazar travels toward Earth, it passes through vast stretches of space filled with gas, dust, and faint structures left over from the formation of galaxies. Although this material is extremely diffuse and difficult to observe directly, it leaves subtle fingerprints on the light coming from the blazar. When light from a blazar encounters clouds of gas along its path, certain wavelengths are absorbed by the atoms in those clouds. These absorption features appear as dark lines in the spectrum of the blazar's light. By studying these lines, astronomers can identify the elements present in the gas clouds and determine their distance from Earth. This technique allows scientists to map the distribution of matter between galaxies. Much of this matter exists in enormous filaments of gas known as the cosmic web. The cosmic web forms the large-scale structure of the universe. Galaxies are not distributed randomly throughout space. Instead, they are arranged along vast filaments of matter that stretch across millions of light-years. Between these filaments lie enormous empty regions known as cosmic voids. By studying how blazar light is absorbed by the gas in these filaments, astronomers can trace the structure of the cosmic web and better understand how galaxies formed and evolved over time. Blazars are particularly useful for this type of research because their jets produce radiation across a wide range of wavelengths. This allows scientists to study the intervening material using many different types of observations, including ultraviolet and X-ray spectroscopy. In addition to revealing the distribution of gas between galaxies, blazars also help scientists study the extragalactic background light, often abbreviated as EBL. The extragalactic background light is a faint glow produced by all the stars and galaxies that have ever existed. Over billions of years, light from countless stars has filled the universe with a diffuse background of radiation. Although this background light is extremely faint, it can interact with the high-energy gamma rays emitted by blazars. When a gamma-ray photon from a blazar encounters a photon from the extragalactic background light, the two can collide and produce an electron-positron pair. This interaction effectively removes the gamma ray from the beam, traveling toward Earth. As a result, very distant blazars appear slightly dimmer in gamma rays than they would otherwise. By measuring how much gamma-ray radiation is absorbed during its journey through space, astronomers can estimate the density of the extragalactic background light. This provides important information about the history of star formation across the universe. Another way blazars contribute to our understanding of the cosmos involves the study of intergalactic magnetic fields. Magnetic fields exist not only within galaxies, but also in the vast spaces between them. However, these intergalactic magnetic fields are extremely weak and difficult to detect directly. Blazars provide one of the few ways to study these invisible fields. When gamma rays from a blazar interact with background radiation in space, they can produce pairs of electrons and positrons. These particles then travel through the intergalactic medium before eventually producing secondary gamma rays. If magnetic fields are present in this region, they can slightly deflect the motion of these charged particles. This deflection changes the direction and timing of the gamma rays that eventually reach Earth. By carefully studying these effects, astronomers can estimate the strength of magnetic fields that exist across vast regions of intergalactic space. These measurements help scientists understand how magnetic fields formed in the early universe and how they evolved as galaxies formed and grew. Blazars are also important for studying the growth of supermassive black holes. The existence of extremely distant blazars means that supermassive black holes were already present when the universe was relatively young. Some of these black holes must have grown to enormous sizes within only a few 100 million years after the Big Bang. Understanding how such rapid growth occurred is one of the major challenges in astrophysics. Several possibilities have been proposed. One idea is that early black holes formed from the direct collapse of massive gas clouds in the young universe. These initial black holes may have been much larger than those formed from ordinary stellar collapse. Another possibility is that early black holes grew rapidly by consuming large amounts of gas from their surroundings. Blazars allow astronomers to observe these early black holes directly. By studying their radiation and the properties of their jets, scientists can estimate the mass of the black hole and the rate at which it is consuming matter. These observations provide important clues about how the first supermassive black holes formed and evolved. Blazars may also help scientists test some of the most fundamental laws of physics. Because the particles in blazar jets move at speeds extremely close to the speed of light, they provide natural laboratories for studying relativistic physics. Observations of blazars can test predictions made by Einstein's theory of special relativity and general relativity. For example, the way radiation is boosted by relativistic motion allows scientists to measure the speed of particles within the jet. These measurements confirm that the particles are moving at speeds exceeding 99% of the speed of light. Blazars also allow scientists to study particle acceleration at energies far beyond what can be achieved in human-made accelerators. The most powerful particle accelerator on Earth, the Large Hadron Collider, accelerates particles to energies of several trillion electron volts. However, particles within Blazar jets may reach energies thousands or even millions of times greater. Understanding how these particles are accelerated remains one of the major challenges in high-energy astrophysics. By studying blazars, scientists hope to uncover the mechanisms responsible for producing the most energetic particles in the universe. Another fascinating area of research involves the possibility that blazars might help scientists search for new physics beyond the standard model. Some theories suggest that exotic particles, such as axion-like particles, may interact with gamma rays traveling through space. If such particles exist, they could alter the way gamma rays from blazars propagate across the universe. By carefully analyzing gamma-ray observations from distant blazars, scientists may be able to detect subtle deviations from expected behavior. Such discoveries could reveal new fundamental particles or forces that have not yet been observed. In this way, blazars serve as powerful tools not only for studying black holes and galaxies, but also for exploring the fundamental laws of nature. Their intense radiation, enormous distances, and extreme physical conditions allow scientists to investigate phenomena that cannot be reproduced anywhere else. From mapping the cosmic web to probing intergalactic magnetic fields and testing the limits of particle physics, blazars provide a unique window into the workings of the universe. In the next part of this documentary, we will explore what might happen if a blazar's powerful jet were ever pointed directly toward our galaxy, and why such an event would represent one of the most extreme cosmic hazards imaginable. Blazars are among the most powerful phenomena in the universe, and their immense energy naturally raises an important question. What would happen if a blazar were pointed directly at us? Because the jets from these objects are so intense and travel at nearly the speed of light, the idea of one being aimed at Earth may seem alarming. While such an event would be extremely unlikely, exploring the possibility helps scientists understand both the scale of blazar power and the potential risks associated with these extraordinary cosmic engines. To understand this scenario, we must first examine the structure of a blazar jet more closely. The jet produced by a supermassive black hole is not simply a narrow beam of light. It is a highly energetic stream of charged particles, mostly electrons and possibly protons, that are accelerated by powerful magnetic fields near the black hole. These particles move outward at relativistic speeds, often exceeding 99% of the speed of light. As the particles travel through space, they emit radiation across many wavelengths. Radio waves, visible light, X-rays, and gamma rays are all produced within the jet. The most energetic part of this radiation is the gamma ray emission, which can carry enormous amounts of energy. Because the particles in the jet move so quickly, the radiation they produce becomes concentrated in the direction of motion through relativistic beaming. This means that most of the energy is focused along the axis of the jet. If that axis happens to point toward Earth, we observe the object as a blazar. Fortunately, the nearest known blazars are located millions or billions of light years away. At such distances, even the enormous energy of the jet becomes relatively harmless by the time it reaches our planet. However, if a powerful blazar were located much closer, perhaps within a few thousand light years, the situation could be very different. In such a scenario, Earth could be exposed to intense gamma-ray radiation from the jet. Gamma rays are the highest energy form of electromagnetic radiation. They have enough energy to break molecular bonds and damage biological tissues. When gamma rays interact with Earth's atmosphere, they can produce cascades of secondary particles and ionizing radiation. A sufficiently powerful burst of gamma rays could significantly affect the upper layers of the atmosphere. One potential consequence would be the disruption of the ozone layer. The ozone layer protects life on Earth by absorbing much of the sun's harmful ultraviolet radiation. If a strong gamma-ray burst were to deplete a large portion of the ozone layer, increased ultraviolet radiation could reach the surface. This could have serious effects on ecosystems, particularly marine life and plant systems that depend on stable environmental conditions. Some scientists believe that gamma-ray bursts from distant cosmic explosions may have influenced Earth's biological history in the distant past. However, even in such cases, the sources would have needed to be relatively close on astronomical scales. The likelihood of a blazar forming near our solar system and directing its jet toward Earth is extremely small. Blazars occur in the centers of galaxies containing supermassive black holes actively feeding on large amounts of gas and dust. Our own galaxy, the Milky Way, contains a supermassive black hole known as Sagittarius A star, but it is currently very quiet and does not produce powerful jets, even if Sagittarius A star were to become active in the future. The orientation of its potential jets would need to align precisely with Earth for us to observe it as a blazar. Given the random orientation of galaxies in space, such alignment would be extremely unlikely. Nevertheless, studying the potential effects of nearby high-energy cosmic sources helps scientists understand the broader impact of energetic astrophysical events on planetary environments. Blazars also help researchers investigate the extreme physics involved in particle acceleration. Within the jet, particles reach energies far beyond what can be achieved in even the most advanced particle accelerators on Earth. The Large Hadron Collider, the most powerful accelerator ever built by humans, can accelerate particles to energies of several trillion electron volts. In contrast, particles inside blazar jets may reach energies millions of times greater. Understanding how these particles achieve such enormous energies remains one of the central questions in high-energy astrophysics. Shock waves within the jet are one possible mechanism. When faster-moving plasma catches up with slower-moving material, shock fronts can form. Particles bouncing across these shock fronts can gain energy repeatedly through a process known as Fermi acceleration. Each crossing of the shock front increases the particle's energy slightly, and after many such interactions, the particle may reach extremely high energies. Magnetic reconnection may also contribute to particle acceleration. As magnetic field lines twist and interact within the jet, they may suddenly snap and reconnect in new configurations. This releases large amounts of magnetic energy, which can be transferred to nearby particles. The result is a sudden burst of acceleration that may produce high-energy radiation, and contribute to the flares observed in blazars. Another fascinating aspect of Blazar research involves the study of neutrinos. Neutrinos are extremely light particles that interact only weakly with matter. Because they rarely interact with other particles, neutrinos can travel across vast distances through the universe without being absorbed. Detecting neutrinos from distant sources provides valuable information about the processes occurring within those sources. In recent years, scientists detected high-energy neutrinos that appear to have originated from a distant blazar known as TXS O506 plus O56. This discovery was significant because it linked neutrino production directly to the processes occurring inside relativistic jets. When high-energy protons within the jet collide with photons or other particles, they can produce pions. These pions then decay into neutrinos and other particles. Because neutrinos travel almost completely unaffected by intervening matter, they carry direct information about the physical conditions inside the jet. The detection of neutrinos from blazars marks the beginning of a new field known as multi-messenger astronomy. In multi-messenger astronomy, scientists study cosmic events using different types of signals, including light, neutrinos, and gravitational waves. Each type of signal provides unique information about the source. By combining these observations, astronomers can build a more complete picture of how extreme cosmic phenomena operate. Blazars therefore represent not only powerful sources of radiation, but also key tools for understanding some of the most energetic processes in the universe. They reveal how supermassive black holes interact with their environments, how particles can be accelerated to unimaginable energies, and how energy can be transported across vast distances through space. Despite their incredible power, blazars remain relatively rare objects. Only a small fraction of galaxies host active black holes producing relativistic jets, and only a subset of those galaxies have jets aligned toward Earth. Yet the ones we do observe provide invaluable insight into the extreme physics shaping the universe. Each new observation brings scientists closer to understanding how these extraordinary cosmic engines operate and how they influence the galaxies that surround them. In the final part of this documentary, we will explore what the future holds for blazar research and how next-generation telescopes may soon reveal even deeper secrets about these violent cosmic powerhouses. Blazars represent some of the most powerful and fascinating phenomena ever discovered in the universe. They combine several of the most extreme features known in astrophysics: supermassive black holes, relativistic jets, intense magnetic fields, and particles accelerated to energies far beyond anything achievable on Earth. Although they appear as distant points of light in our telescopes, blazars are actually enormous cosmic engines capable of releasing staggering amounts of energy. Understanding blazars requires scientists to study many different branches of physics at once. Gravity plays a central role because the process begins with a supermassive black hole whose mass may reach billions of times that of the Sun. The immense gravitational pull of the black hole draws surrounding gas and dust inward, forming a rapidly rotating accretion disk. Within this disk, matter moves at incredible speeds while heating to extreme temperatures. The intense radiation emitted from the disk can illuminate the central region of the galaxy and outshine billions of stars combined. At the same time, powerful magnetic fields interact with the rotating plasma in the disk. These magnetic fields twist and stretch under the influence of the black hole's gravity and rotation. Eventually, some of the energy stored in these magnetic fields is released in the form of relativistic jets. These jets are narrow streams of plasma launched away from the black hole along its rotational axis. The particles inside the jets travel at speeds extremely close to the speed of light, carrying enormous amounts of energy across vast distances through space. In most galaxies, these jets point in directions unrelated to our line of sight. But in the case of a blazar, one of the jets happens to be pointed almost directly toward Earth. This alignment creates a powerful observational effect known as relativistic beaming. Because the particles in the jet are moving so quickly, the radiation they emit becomes concentrated in the direction of motion. As a result, the light reaching Earth is dramatically amplified. This is why blazars appear so extraordinarily bright, even when they are located billions of light-years away. The radiation produced by blazars spans the entire electromagnetic spectrum. Radio waves reveal the structure of the jets across enormous distances. Visible light and ultraviolet radiation originate from energetic particles near the central engine. X-rays and gamma rays provide information about the most extreme processes occurring near the base of the jet, where particles are accelerated to extraordinary energies. Observations across these different wavelengths allow astronomers to build detailed models of how blazars operate. One of the most remarkable aspects of blazars is their ability to accelerate particles to enormous energies. Within the relativistic jet, particles can be boosted to energies millions of times greater than those produced in human-made particle accelerators. These particles produce high-energy radiation through interactions with magnetic fields and photons. Understanding how this acceleration occurs remains one of the major challenges in astrophysics. Shock waves moving through the jet likely play an important role, as they can repeatedly accelerate particles through processes similar to those observed in supernova remnants. Magnetic reconnection events may also contribute to particle acceleration by releasing stored magnetic energy within the jet. Another fascinating discovery in recent years is a connection between blazars and high-energy neutrinos. Neutrinos are extremely tiny particles that interact only weakly with matter. Because of this, they can travel across vast distances through the universe without being absorbed. In 2018, scientists detected a high-energy neutrino originating from the direction of a distant blazar. This discovery marked an important milestone in astronomy. For the first time, researchers were able to connect a specific cosmic source with the production of high-energy neutrinos. The detection suggested that the jets of blazars accelerate not only electrons, but also protons and heavier particles. When these particles collide with photons or other particles within the jet, they can produce neutrinos and other secondary particles. This discovery opened the door to a new era of multi-messenger astronomy, in which scientists study cosmic events using multiple types of signals, including light, neutrinos, and gravitational waves. Blazars also help astronomers explore the structure of the universe itself. Because they are so bright, blazars can be observed at enormous distances. The light we see from some blazars today began its journey billions of years ago. As this light travels through space, it passes through clouds of gas and dust located between galaxies. These clouds absorb certain wavelengths of light, leaving distinctive patterns in the blazar's spectrum. By analyzing these patterns, astronomers can map the distribution of matter across the universe. This technique allows scientists to study the large-scale structure known as the cosmic web, a vast network of filaments connecting galaxies across immense distances. Blazars therefore act as powerful cosmic lighthouses, illuminating the invisible structures that fill intergalactic space. Another important area of research involves the study of intergalactic magnetic fields. Magnetic fields exist not only within galaxies, but also in the vast spaces between them. However, these intergalactic magnetic fields are extremely weak and difficult to detect directly. Blazars provide one of the few ways to study these invisible fields. When gamma rays from a blazar travel through space, they may interact with background radiation and produce pairs of electrons and positrons. These particles then produce additional gamma rays as they move through space. If intergalactic magnetic fields are present, they can slightly deflect these particles. By studying the resulting patterns of gamma rays, astronomers can estimate the strength of magnetic fields that exist across enormous regions of space. These measurements help scientists understand how magnetic fields formed in the early universe and how they evolved over billions of years. Despite the progress made in understanding blazars, many questions remain unanswered. Scientists are still working to determine exactly how jets are launched from the vicinity of supermassive black holes. The details of particle acceleration within the jets remain an active area of research. Astronomers are also trying to understand how blazars evolve over time and how their activity influences the growth of their host galaxies. Future telescopes will play a crucial role in answering these questions. Next-generation observatories will be able to detect fainter and more distant blazars, providing a more complete picture of how these objects are distributed across the universe. Improved gamma-ray telescopes will allow scientists to study the highest energy radiation emitted by blazars with greater precision. Meanwhile, neutrino detectors and gravitational wave observatories will open new windows into the extreme physics occurring near supermassive black holes. Together, these instruments will help reveal the complex processes that power these extraordinary cosmic engines. Blazars remind us that the universe is capable of producing phenomena far beyond anything we experience on Earth. They show how gravity, magnetism, and relativistic physics can combine to create some of the most violent events in the cosmos. From their brilliant jets to their unpredictable flares, blazars continue to challenge our understanding of the universe and push the limits of modern astrophysics. As scientists continue to study these remarkable objects, each new discovery brings us closer to understanding how the most powerful engines in the universe truly work. And somewhere in the distant darkness of space, countless supermassive black holes continue to launch their relativistic jets into the cosmos, silent reminders of the incredible forces shaping the universe.